Alright, so today we're going to be going over organic compounds and basically just trying to gain an understanding of how their structures are actually put together. So first of all, before we get going, there's a few rules which will just make our lives a lot easier, and when we're trying to interpret these structures, there's some basic rules of thumb that are followed most of the time. When we get to more complicated structures at the end of the semester, these won't always hold, but for right now, they work perfectly well. So the basic rules are that carbon is always going to have 4 bonds, nitrogen is always going to have 3 bonds, oxygen is always going to have 2 bonds, hydrogen has 1 bond, and all the halogens over here, they also have 1 bond as well. And if we go back to the periodic table here, we can see that, here, this is 4, 3, 2, and then everything here is 1. And then, of course, on the other side, we have hydrogen here, which is also 1 as well. Occasionally, you might see a sulfur in there. The sulfur will act just like the oxygen. It will also have 2 bonds. The phosphorus, it depends. I mean, it could have just 3 bonds, although sometimes you can actually get expanded octets with 5 in there. So we're not going to worry about anything that complicated. But the basic thing is right here, 4 for carbon, 3 nitrogen, 2 oxygen, 1 for the halogens, and then also 1 for the hydrogen. All right, now all these bonds here are going to be covalent. Okay, so these are not ionic bonds. There's no anions or cations. This means that, our electrons are shared equally here. All right, so we're going to be drawing these out. Most of us are not artists, so we're going to try to draw this in the simplest method possible. It doesn't accurately represent what the molecule looks like, but, we'll show what the molecule does look like and, how these projections actually work here. All right, so first up, we're going to start at the simplest hydrocarbon, and hydrocarbons are compounds composed of hydrogen and carbon. Okay, so hydrocarbons can just contain hydrogen and carbon in them. And the simplest one, we've seen this before, is methane. All right, and the way we draw this out, again, when we saw this before, just like so. This is where I'm getting into the fact that, the structures that we're drawing do not accurately represent what these things really look like. If you just look at this, you may think that methane is a flat molecule, and that is very wrong. It's a 3-dimensional molecule. It's what we call a tetrahedron. What this actually looks like, and this is the way that you can draw it to represent more of a 3-dimensional structure here, is like this. So here's your carbon. We draw 1 bond up like this, 1 bond off to the side like that, and a little wedge here. So this gives more of a 3-dimensional feel for this. And you'll notice that, I have like 3 different types of bonds. Okay, this is again to give that 3-dimensional feel. So these 2 over here, these are in the plane of the paper. So what this means is that, if we draw this thing, the hydrogen, the carbon, this hydrogen here, they all lie flat with the table. So they're all lying here. This one is going behind the paper, right? So that's going behind, and this one over here is going in front. So this is what it's doing to help give more of a better representation of how this thing looks. So again, it's a 3-dimensional molecule. These lie in the same plane. One's sticking out, and one is going behind here. So here we have a molecular model of methane. So the carbon is the black, and all these white balls are the hydrogen atoms. And just to give you an idea how this thing actually looks, 3-dimensionally, so I'll just, rotate this around here. Now, another way we can draw this, which, again, may help just a little bit here, is if I draw this as a little cube, and actually we can figure out what these bond angles are between the carbon and the hydrogens if we draw this out as a little cube. It's kind of cool. So here's my little cube like this. Now, what we're going to do here is put my carbon in the middle of the cube. Okay, so there's my carbon in the middle of the cube. Then what we have to do is place my hydrogen atoms, and here I'll just draw them as little dots. Okay, so we can put like 1 hydrogen here, 1 hydrogen over here, and then we can put 1 hydrogen over in this corner and 1 hydrogen on that corner. So right here, this is going to be attaching to my carbon this way. There's going to be this one's attaching to the carbon up here. The one that's attaching to the carbon over here, and then there's the one which is coming out this way over here. Okay, so that's what's going on with this. Now we can actually use this to figure out what the bond angle is, because it's just a little simple matter of little trigonometry. These points here are just going to be corners of a cube, and what we've done here is that the carbon is at the origin. So in other words, the carbon is here at 0, 0, 0. Okay, so we just put the carbon there. And then as for the hydrogens, my little red dots, these are just going to be at some variation of plus and minus 1. Okay, we're not going to worry about what they actually are, but it's going to be, you know, something like 1, 1, 1, minus 1, minus 1, 1, like this. So basically you're just going around and moving these things there. So they're going to be at some corners of the 1, 1, 1s. When we calculate, you know, this bond angle, so this is what we're going to be interested in right here. Basically, this bond angle is what we're interested in, or this bond angle, or that bond angle, or that bond angle. They're all equivalent in this case. We have, you know, a nice little triangle. Okay, now we're going here from 0, 0, 0 to 1, 1, 1. That means that this length over here is going to be the square root of 3, because we're going from 1, 1, 1 to 0, 0, 0. The length of that, you know, vector is going to be the square root of 3, right? 1 squared plus 1 squared plus 1 squared, take the square root. That's where we get that. And then the same thing, you know, for all these other blue lines, are the square root of 3. Now, as for the length between these two dots, well, again, that's going to be like 1, 1, 1 to minus 1, minus 1, 1. So if that's the case, we essentially have, again, you know, a nice little triangle. And the length between these two dots over here, draw it that way, or I could draw the one up there, is going to be 2 times the square root of 2. So that's my triangle, right? The square root of 3, this is 2 square root of 2, and this side over there is also the square root of 3. So let's just draw this as a nice little triangle here. So there is this 2 square root of 2, and then here is going to be my blue line, like so, and that's going to be the square root of 3. That's the square root of 3. So of course, you know, there's my carbon, here's my 2 hydrogens like that. Now we have, of course, an isosceles triangle. We can bisect this triangle. So I can bisect that triangle. So now this is going to be a nice little right triangle. And that means if I bisected this isosceles triangle, that's going to be the square root of 2. That's going to be the square root of 2. Square root of 2, my hypotenuse is the square root of 3. And we can easily figure out what my angle is here. And we're going to call that theta over 2, because of course this was theta, what we were actually looking for. So that's, since we've bisected that angle, that's going to be theta over 2. And now we can go here, and remember your SOHCAHTOA, right? You know, the sine is the opposite over the hypotenuse. So here, the sine of theta over 2 is equal to the square root of my opposite, which is the square root of 2, over my hypotenuse, square root of 3, which is, you know, equivalent to square root of 2/3. Then you just go along, figure out the inverse sine of that, 2 over 3, square root, inverse sine. So that works out to be 54.7 degrees, but of course that's theta over 2. So then I multiplied this by 2, and I get, you know, the very famous, what we call 109.5. It's 109.47, but this is how many degrees that bond angle is right there. Okay, so your theta, which is our bond angle, is at 109.5 degrees. Okay, so that's the bond angle in the carbon when we're dealing with, you know, nice little single bonds here. We're going to see it's actually 120 if we're dealing with double bonds, but for these nice single bonds like this, in general, carbons that have 4 different bonds like this, this is going to be the bond angle between them. And this is, you know, for this one, for this one, for this one, for this one. So all of the bond angles are equivalent. It's a nice symmetric molecule, and that's of course what we do call the tetrahedron. Okay, now we can start looking at some more hydrocarbons, and we're just going to look at the few easy ones. We're not going to get into, you know, too much subtleties about the naming here, because that, you know, we can literally spend weeks going over all the naming conventions here. We just want to introduce you to some common ones that, and things that, you know, you probably have heard of, and, you know, just put a molecule to a name for these. So we've seen methane. Next on the list is what we call ethane. And we can easily just write this as CH3CH3. So this is the nice little shorthand for that, and this is called ethane. All right, and here we have an ethane molecule. So this actually does rotate around, and actually the most stable configuration of this would be if I orient the atoms like this. So actually there's this whole stuff they talk about, barriers to rotation, if you're looking at this, and this can actually rotate around. But the most stable configuration is actually oriented this way. So now all the hydrogen atoms are as far away as possible from one another. So this is, you know, the most stable. This would be a higher energy because now, you know, these things are a little bit closer, there's some repulsion going on, there's a little bit higher potential energy. So this would actually be called, you know, an eclipsed conformation, but if I rotate it just like so, this would be a staggered conformation. And this is, just how the molecule looks in 3 dimensions as we rotate it around. And we can add another carbon here, and we can have 3 carbons now. And this is going to be CH3, CH2, CH3, and this is called propane. Now, propane is also related to a molecule called propanol, and you probably have some of this in there. So if you oxidize this and make an alcohol from it, we get here, which could be called 2-propanol, and that's the scientific name for this, or you may probably know this as isopropyl alcohol. Okay, and you probably have a bottle of this, in your medicine cabinet or something. It's a, very useful, very versatile stuff. Of course, do not drink this. That would be very bad for you. But this is what that molecule actually looks like. Now, the other interesting thing is if you actually take this molecule and oxidize it further, this is called acetone. And of course, acetone is what's commonly used as nail polish remover. So this is, another very common molecule. Now, what you probably are starting to notice is that, writing out all of these H's is very tedious and very time-consuming. So what the chemists do is generally just kind of leave all of the H's off, because in organic compounds, there tend to be a lot of H's. And we do know from our rules that we start off with here, that carbon's always going to have 4 bonds, hydrogen is just going to have 1 bond, so we can actually simplify these structures based upon that, and we could just easily write this as either a string of carbons, like that, and then just say, well, the hydrogens are understood to be there, and we could also do it like this, or like this. And all of those essentially communicate the essence of what is actually going on. Now you'll notice here for the OH that H is on there. You don't want to just put a single bond on an oxygen and then just have it hang in there. It's just bad form. You want to have the hydrogens. If only if it's something that is carbon, then you leave the hydrogen off. But if it's the nitrogen or the oxygen, then you definitely have to include that hydrogen there if it's actually there, because there could be some ambiguity. Now, again, drawing all these little carbons out can get a little tedious, so there's even something that they simplify even further. They just make little lines like this, and that's actually equivalent to that. We can also write, the isopropyl alcohol as something like this, the OH, and then for the acetone, go like this with the double bonded oxygen like that. Okay, so again, these are another equivalent way of writing that. So for these little line diagrams and little stick diagrams, this is actually the way that you will usually see organic compounds represented, because it's simple, it lacks a lot of clutter, and it's just a lot easier to do it that way. What we have here at every endpoint, that's going to be a carbon, and at every vertice, that's going to be a carbon. So carbon, carbon, carbon. And then, of course, here we have a carbon, 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 carbon. And then on the ends, you just start sticking your hydrogen. So again, because carbon has 4 bonds, that means that this point right here, and the reds are just going to represent the hydrogens coming off. There's going to be 1, 2, 3. And then this one, is bonded to 2 things, so there can only be 2 hydrogens actually coming off like this. And then this one, since it's bonded to 1 thing, there can be 3 hydrogens coming off. And that's exactly what we see up there, right? And again, over here, the 2 endpoints are going to be the same, because those can hold 3 hydrogens. And then this point over here, this carbon is bonded to 1, 2, 3 things. Therefore, there can only be 1 hydrogen that comes off. And then over here on the end here, this carbon does same thing like we saw the other 2 times, same for that one. But then this one in the middle, this is bonded to 1, 2, 3, 4. There's no room for any extra hydrogens on there. So that's how you can just take the stick diagram, and then you can easily figure out exactly where the hydrogens go, because you know that every carbon here has 4 bonds. So that's why you know that that's going to happen. If there's some reactive intermediate where the carbon only has 3 bonds or 5 bonds or something, well, then you would just explicitly write it out. But those are fairly rare. Most of the time, it's understood that carbon has the 4, and then you just continue on with that. So that's the propane. Now, another one that you may hear of is going to be the butane. So if you have a butane lighter, and this is going to have 4 carbons in it. So 1, 2, 3, 4. Right, and I'm not going to write all the little hydrogens, but again, equivalently, we could just write something like that. So 1, 2, 3, 4. That's equivalent to my carbon diagram. Again, that would be like a CH3, CH2, CH2, CH3. Or you might even see it like this, CH3, then with a CH2, 2, CH3. So what this point right here is, the CH2 just means you repeat that twice. And again, this is a little extra simplification because sometimes you're dealing with chains that are 10 or 20 of these things long, and it's just a lot easier just to put a little subscript there rather than writing it out 10 or 20 times. Then of course we could have here pentane. And if you remember from the bimolecular compounds, pent means 5. So unsurprisingly, that's just going to be 5 carbons. 1, 2, 3, 4, 5. So that's going to be the pentane. And again, hydrogens are already on there. Another one, you also have hexane and heptane, but one that you're probably familiar with is octane, especially if you're dealing with anything with cars. So octane, that's going to be 8 of these. So that's 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Again, with the extra hydrogens on there. Now, with these more complicated ones, now for the one over here, these are just going to be in a nice straight line. There's no way you can change these around at all. But for these more complicated ones, you can actually put the carbons in even different orders, and these are called isomers. All right. So for instance, if I take here the pentane like this, so different, and these are going to be different isomers, and these do not chemically interconvert. These are separate molecules, their own unique properties. I can very easily write here 1 and then stick a carbon off like that, and that's going to be a different isomer. I could also have over here like that, okay, and that is yet another isomer. You might be wondering, could I have put this carbon over on that one and left that one blank? Then that would actually be the same, because that would just be the mirror image of this. All right, so you don't want to double count when you're dealing with these. But these are, there's 3 isomers here for the pentane. So there's different ways of actually arranging these. And as you go towards larger ones, especially like octane, you get many, many of these. And I'm not going to try drawing them all out. There's just a lot of them. They branch, and you can get many, many complicated molecules actually coming off. And that's why crude oil has so many different molecules in there, because you have all these different isomers actually forming in there. One other thing to note about all these compounds that we've been looking at so far, these are what we refer to as saturated compounds. And by saturated, this means that the carbon is, has 4 bonds, and there are no double bonds or triple bonds in there. These are all single bonds. Okay, so that's what we mean by saturated. Of course, you've probably heard of saturated fats. That's what it's referring to, where there are no double or triple bonds in these molecules. So all of these things right here are single bonds. We'll be looking at double bonds in a little bit here. There's also other ways we can arrange the carbon atoms to make different isomers as well, and we can even make rings of these. Okay, so just like this. That's just a ring of carbon atoms in the shape of a triangle. So that would be a CH2 group up here, a CH2 group over here, and a CH2 group over there, and then that would just form. That would be called what we call cyclopropane. You can even go, making a little square of carbon atoms, right? Or you can make a little pentagon of carbon atoms. Or what's actually very common is seeing a little hexagon of carbon atoms. All right, and that would be called cyclohexane. All right, now I also mentioned that there are molecules that can have double bonds and triple bonds on them. The simplest one that we have here, and by the way, if we have here a double bond, so in other words, a double carbon-carbon bond like this, this is what we call an alkene. The simplest one is going to be ethylene. So that's how you would write it out, and this is of course called ethylene. It's also, its technical term should be called ethene. But most people just call it ethylene because it, again, spelling is very important. Ethane, E-T-H-A-N-E, and here is ethene, E-T-H-E-N-E. So just a little subtlety. Now, an interesting thing about these double bonds is that they are not very flexible, meaning that if you have a molecule like this, it does not start rotating around it. All right, and here we have an ethylene molecule, and you'll notice the difference here compared to the ethylene molecule, or the ethane molecule that we had earlier. See, this ethane molecule could rotate around, right? So this can rotate around. It's three-dimensional, in its versions. Meanwhile, this ethylene with the double bond is actually two-dimensional. So all these hydrogens and carbons lie in the same plane. All right, and also this does not rotate around. So this, these are very different molecules. They obviously have different properties, and they are oriented differently there. Okay, so anyway, this is the ethylene. Well, actually, the alkenes like this, at least the local area here, is going to be flat. So these bond angles are all going to be, approximately 120 degrees. Okay, so that's going to be about the same. That's going to be about the same. 120 plus 120 plus 120 is 360, of course, a circle, right? So this is going to be a flat molecule like this. Now, an interesting thing here is because this stuff doesn't actually rotate around, if I have a molecule like this and this, okay, these do not interconvert. Okay, so these do not go between one another. All right, so these molecules, they have their own unique properties, different melting points, different boiling points, different densities. So these are very, very important differences here. And the way that they name these differences is if the parts are actually on the same side, like this, so you see the CLs are on the same side here, this is called a Sis Isomer. And this one, because they're on opposite sides, is called a trans isomer. Why is this important? Many of you have heard of the evils of trans fats. That's what they're referring to. A lot of the fat molecules that you eat, have many, many double bonds in them. And when you have a natural fat, like olive oil or vegetable oil, these are cis fats. They look like this, and of course it's not with actual chlorines, and they are much, much longer. The basic thing is the same, is that you have the molecule looking kind of like this, and it has a particular orientation because parts of the fat molecule are on the same side. Meanwhile, with the trans, you get a different shape for this entire fat molecule, and then it does bad things to your body. It screws up your cholesterol and does other bad stuff to there. And this actually occurs because when you take normal oils, which have low melting points, and they go and hydrogenate them. Basically, they're adding hydrogens across these double bonds. Those hydrogens are added to the double bonds, and occasionally some hydrogens actually leave. The trans isomer tends to be more stable because it's not quite as crowded as the cis isomer is. So because it's less crowded like this one's a little bit more stable. It forms, and then it got into the food until people started paying attention to it because they realized it was actually very bad for you. Next up are the alkynes. So here, if we have a triple carbon triple bond like so, and the simplest of this is going to be acetylene. And actually, this is a linear molecule. So this bond angle here, that's just 180 degrees. Okay, so this is a linear molecule called acetylene. Also, it is called ethine. But again, most people just refer to that as acetylene. Now, remember we were just talking a few minutes ago about these different ring structures. Well, these rings can also have double bonds in them. Not the triple bonds, because that's a lot of, well, for some reactive species you can have triple bonds, but most of the time you'll just see double bonds actually form inside of these rings. And there's one very, very important one. And this is actually a different class of molecules. These are what we would call aromatic molecules. But here, this is going to look like this. So again, this is a hexagon, and it has alternating single and double bonds like this. And the formula for this is C6H6, and this is called benzene. And this is a flat molecule. And just to show why this is so important is that because of these alternating single and double bonds, we can't say that, this is actually a single bond, or this is actually a single, this is actually a double, that's a single. What's actually going is that these bonds are actually switching between one another really, really fast in a phenomenon known as resonance. So it's actually going back and forth between this one and this one. Screwed up a little bit there. So it's basically just switching back and forth like this, and occasionally you will see it also written like this, with a little circle in it, and that's equivalent way of writing this. And then just to demonstrate exactly what this does look like, in case you actually see it someplace else, again, if we look at this, remember that all the little hydrogens have to come off, and every carbon has 4 bonds on it. Well, here this is going to be 1, 2, 3, so that means there's going to be 1 hydrogen sticking out like here, And same here, 1, 2, 3, one hydrogen sticking out. And basically for all of these, you're going to have one hydrogen sticking out. And again, that's why you're going to have C6H6. And then you can put like little substitution, little rings or little other molecules and stuff on the outside of there. So just to draw what benzene would look like with the carbons and the hydrogens there, this is what it would seem like. And all these bonds are going to be 120 degrees. So that's 120, that's 120, that's 120. So it's again a nice flat molecule. And because of this resonance structure that is actually going on, these are a different class of molecules, and these are termed aromatic. Now, aromatic, you may think that means that the molecules smell. Initially, that is why historically these were named aromatic molecules. But now there are many molecules that contain benzene rings in there that do not have an actual odor. But for historical reasons, we still do term these aromatic molecules. So what we've talked about so far is, the carbon chains and everything, but the thing is that makes organic chemistry so interesting is that we can put functional groups on there. And these functional groups give the molecule its own unique properties, and every different little functional group, they're like a whole new class of molecules, and they have similar odors, similar densities, similar boiling point trends, similar densities, melting points, and everything else. So because of these things, you can actually get a lot of useful information from there just by looking at it and figuring out why these things actually behave the way they do. So there's a few of these we've already seen, the double bonded, right? So remember that was the alkene or alkenes. We've seen the triple bonded ones, so we've seen those two. We've also seen the alcohol one. Remember we were talking about ethanol, so we've seen that one before, and also when I mentioned, where'd he go? And also when I was mentioning here the isopropyl alcohol, that's that OH group over there, okay? Now again, if you have this OH and it is bonded to a carbon, that is an alcohol. This is not hydroxide, okay? So don't confuse, the OH and think it's a base or a hydroxide. It's completely different if you're dealing with something attached to a carbon like this. Another one that we've already seen as well is this one. And this is what we call an aldehyde. All right, and you probably remember that when we were talking about the ethanol and how it oxidizes because the alcohol dehydrogenase, it becomes acetaldehyde, which of course causes the hangover. And of course, if you drink methanol, it oxidizes to become formaldehyde. So these are all aldehydes over here if they have that particular functional group. Related to the aldehyde is something called a ketone. And we did actually see a ketone here a few minutes ago when I drew out acetone. All right, so this is the simplest ketone actually. So right there, there's the carbon double bonded to the oxygen in the middle like this. Another one that we also saw when we were talking about acetic acid, of course, and we've mentioned this multiple times, is if we have here the COOH. And that's, of course, going to be an acid. And I should say carboxylic acid. All right, so that's a carboxylic acid group. All right, and then there are some that we haven't talked about before, but we'll mention them now. There's also, if we have here carbon with an oxygen with a carbon like this, this is what we term an ether. So if you put ether to knock someone out, or it's very commonly used as a solvent. Ethers have very low boiling points. They're very volatile. They're not very reactive, which is kind of good, but you always have to be cautious with them because if you're not careful, they can explode on you if you're not careful with that. Another one, which we actually can get here, if I combined, so if I go back up here, if I combine an alcohol and a carboxylic acid, and this is a very, very common reaction that they do in organic chemistry labs, and really it's one of the students' favorite reactions because this is one of the few times that the lab actually smells really nice, is if you react an alcohol and a carboxylic acid, you get something which is known as an ester, and it looks like this. And over here you might say, well, that looks very close to the carboxylic acid. Well, yeah, because it came from that portion here, but now this is going to be bonded to some other carbons out here. This is going to be bonded to some other carbons like this. And this is what we call an ester. And esters are a class of molecule that smells very nice. The whole reason that your bananas smell nice is because of an ester. Your pineapple smell because of an ester. Your tutti frutti bubble gum smells because of an ester. So there's all those. Wintergreen is an ester as well. So there's a whole bunch of these nice smells that come from esters. All right, and then now we're going from the nice smells. We're going to something very nasty now. This is going to be called amines. So this is where we have a nitrogen basically bonded to something like this. And really the simplest one that we have here would be what's called methylamine. So that's going to be a carbon like this. So there's the methyl portion, then with a nitrogen going off like that. So this is called methylamine. All right, and these are amines. And amines stink. They basically smell like fish. They're related, as you can probably just look at this. It's related to like ammonia molecules, right? Ammonia is NH3. Well, this is basically a methyl substituted ammonia. So it has a very fishy ammonia-like smell that is very unpleasant, and that's generally a hallmark of the amines. So if you're using some of these things, you try to avoid as much as possible because they really do stink. In general. So esters, very nice. Amines generally stink. And another one here we can actually have is related to the amines, and it's similar to the ester, but now if we have, instead of an oxygen here, we have a nitrogen, we have what's called an amide. All right, so this is called an amide. All right, and these are used very often in proteins. All right, so proteins are made of amino acids. And here there's your amino part, there's your acid part, so they have like both of these inside of the amino acid there. And then when they react, the way they bond is by forming these amide bonds. All right, and that's what holds proteins together. It's all these little amide bonds connecting each little amino acid group, and then you get a long protein like hemoglobin. All right, and then you can also get more complicated molecules as well. A number of organic molecules, even though, it seems like we're just limited to only a few building blocks, carbon, hydrogen, oxygen, nitrogen, and a couple other things which might be used in there. There's a whole reason it's called organic chemistry, and it has its own subset, and the reason that you would take 2 semesters plus of organic chemistry if you are a chemistry major is because there are literally millions and millions and millions of compounds. But if you look at the other 117 elements, the number of compounds that they make is far less than the number of organic compounds that are possible. And that's about all I want to say on organic chemistry.